Written in the 2nd century CE, Claudius Ptolemy's Mathematica Syntaxis, better known as the Almagest, became the most important text in mathematical astronomy for the next 1500 years. But despite the historical significance of this text, it's nearly impossible to find detailed information on how its models were derived and functioned. So much so that when I began studying historical astronomy, I decided it was best to sit down and work through it myself. So, in this series, I'll share what I've learned about one of the most important astronomical texts of all time. I'll begin by addressing things conceptually, so viewers that aren't interested in the detailed mathematical workings can get an appreciation for Ptolemy's work. With that out of the way, I'll then explore select mathematical topics, taking the understanding from conceptual to functional, allowing viewers to understand how the models were practically applied. In this video, I'll be exploring Book 6. In this one, Ptolemy combines the lunar and solar models discussed previously to examine eclipses. Then, since it sure would be inconvenient to have to calculate the position of the sun and moon for each day to see if an eclipse occurs, he discusses how frequently eclipses can occur to only calculate when absolutely necessary. So, join me as we explore how Ptolemy defined astronomy before the telescope. Before we jump in, I want to warn everyone that even though I try to keep this series pretty conceptual, eclipses are complicated. Correspondingly, Book 6 is one of the most challenging books in all of the Almagest, as we're going to have to keep track of a lot of details. The result is that it's easy to get lost in the weeds. If you start to feel overwhelmed, feel free to skip to the end for the TLDR. There's a convenient index in the description to help. But with that out of the way, let's get started. As noted, Book 6 is dedicated to a discussion of eclipses. In principle, we already have everything we need to determine if an eclipse will happen at a given time. Calculate the position of the sun and moon. If the moon is directly in front of or directly opposite the sun, then you'll have an eclipse. But how do we actually use that to predict eclipses? After all, calculating the positions of these objects is not an easy task. And the moon moves so fast, you need to calculate both of their positions multiple times per day to approach eclipse prediction through brute force. Ptolemy is aware of how ridiculous doing so would be, and in Chapter 1 tells us that there's obviously a better way. He reminds us that eclipses only happen at conjunction and opposition, collectively known as syzygies. So we don't need to worry about computing anything when the sun and moon are nowhere near these. Thus, much of Book 6 is going to be dedicated to a determination of the true conjunctions and oppositions. However, the timing of true syzygies is complicated by the fact that both the sun and moon have their own independent anomalies. Thus, we'll begin by examining the times and places of the mean conjunctions and oppositions, together with the position of the moon in anomaly and latitude at these mean times. This will give us a quick check to determine the times when eclipses might be possible, instead of performing useless calculations where the sun and moon are nowhere near a syzygy. And, as usual, Ptolemy has constructed tables for this purpose. He explains how these tables were constructed in Chapter 2. He begins by determining when the last mean conjunction occurred prior to his epoch date. This is relatively easy to do since, in Book 4, he determined the elongation at the start of the epoch. So, all he needs to do is divide that by the amount the mean elongation increases each day to know how many days it has been since the last conjunction. It was about 5 days and 19 hours prior to the start of the epoch. Then, Ptolemy can subtract that from the length of a synodic month, i.e. a lunation, to determine when the first conjunction in the epoch was. He finds that it occurred about 23 days and 18 hours after the start of the epoch. But since months don't have a day zero, that means it occurred on the 24th of that month. We can then ask how far the sun and moon moved around their various circles to determine their positions during that first conjunction. Ptolemy is also interested in the oppositions, though. As such, he determines the date and position of the first opposition since the start of the epoch. Next, Ptolemy notices that after a period of 25 years, the first mean conjunction or opposition of each year will fall at almost exactly the same day and time, shifting forward by only about 1 hour and 7 minutes in each 25-year cycle. Thus, the rows in the table are moved forward by 25 years each line. Of course, the positions of the sun and moon about their circles aren't in exactly the same position, so they require a bit more computation, but ultimately, Ptolemy includes 44 25-year cycles in the table, giving the day, time, and positions of the sun and moon about their circles at the start of each. However, we need to drill down a bit more than every 25 years, so Ptolemy also creates another table which will allow us to add anywhere from 1 to 24 years to the 25-year periods. However, things get a bit trickier for Ptolemy here. In most years, there are 13 complete lunar cycles, but sometimes there are only 12. Thus, Ptolemy has to carefully consider where in the cycle the sun and moon are to know how much the sun and moon will have moved in a full year period. Having completed that, Ptolemy finally makes a table allowing us to drill into individual synodic months. The tables are then presented in Chapter 3. Let's pause a moment to determine what we have so far. Right now, we've developed a set of tables that tells us the position of the sun about its circle, the moon about its epicycle, and the moon from the northern limit of its inclined circle, all at the moment of mean syzygy. However, mean syzygy doesn't mean that the sun and moon are actually at the same ecliptic longitude. The anomalies will almost certainly mess things up for us. So the real question we need to answer is, how do we determine the true syzygy? The moment when, anomalies considered, the sun and moon are either in conjunction or opposition. Fortunately, we already have the important figures we need to be able to quickly determine the anomalies using the tables in the previous books from the table that we just made. Ptolemy recommends calculating these anomalies first, and if the amount of anomaly doesn't match, then there wasn't an eclipse, right? Well, not quite. It only means that there was no eclipse at the moment of mean syzygy, but we still need to figure out when the true syzygy was, taking into account the anomalies. To understand, let's again apply the anomalies to solar and lunar positions. But this time, I'll do it for some point in time before the mean conjunction. At this particular moment, if I apply the anomalies to their mean positions, they work together in such a way that they bring the sun and moon together and do cause an eclipse. This is the true conjunction. However, syzygy, mean or true, alone doesn't mean that there's an eclipse, as syzygies are defined using lunar longitude. Lunar latitude is also important. Obviously, we could simply calculate that, and if it is 0, then there's certainly going to be an eclipse. But the moon can be slightly above or below the ecliptic, and we can still get an eclipse. For solar eclipses, this will just mean that it's partial. For lunar eclipses, the shadow of the Earth is sufficiently large that the moon can be some distance above or below the ecliptic and still result in a complete lunar eclipse. Furthermore, because the Earth's shadow has a width in ecliptic longitude, this means that it's possible to have a lunar eclipse just before or after true syzygy. So we'll need to explore how far around syzygy eclipses can occur. But I'm getting ahead of myself. The true purpose of this chapter was to explore how to determine the true syzygy from the mean. And conceptually, Ptolemy's approach is pretty simple. Knowing the time of mean syzygy, we can calculate the differences of the true position of the sun and moon for solar eclipses, or the anti-solar point and the moon for lunar eclipses. In short, calculating the distance between the two. We can then consider their individual speeds to determine when they would have been at true syzygy. It's not quite as straightforward as that because the moon's anomaly is sufficiently large that we need to take it into consideration. But Ptolemy provides instructions on how to do that as well. In Chapter 5, Ptolemy digs deeper into the question of how to determine how far from the nodes eclipses can occur. To begin, Ptolemy needs to get a better understanding of the angular size of the moon. Back in Book 5, Ptolemy determined the angular size of the moon at its furthest distance, when it's at its maximum distance on its epicycle and the deferent. But what about when it's closest? You might be thinking that because we also calculated the actual size of the moon and all the components of the lunar model in Book 5, that we could just use this to geometrically determine the angular size of the moon at its closest point. And you'd be right, but that's not the method that Ptolemy uses, probably because doing so would return results that are so obviously at odds with observations that they couldn't be taken seriously. Ptolemy even states that it is safer to demonstrate this kind of parameter from the actual phenomena, likely indicating that he is quietly aware of how ridiculous his own model is due to how close it brings the moon. So, instead, Ptolemy repeats the calculation he did in Book 5, in which he determined the angular diameter of the moon using a pair of eclipses when the moon was near its closest point, and finds that the lunar diameter was 35 minutes and 21 arcseconds, only about 4 minutes of arc larger than it was at its furthest distance. And from the same calculation, he can also determine the angular size of Earth's shadow at that distance, and he finds that, at this closest distance, its diameter is approximately 2 3/5 times the diameter of the moon itself. This is exactly the same result he reached for the moon at its furthest distance. But keep in mind that the moon also appeared smaller at that greater distance. Thus, the actual angular width changes too, as we should expect. And now that Ptolemy knows the angular diameter of the Earth's shadow at the moon's closest and furthest positions, along with the apparent diameter of the moon at each of those, he can ask how far above or below the ecliptic the moon could be such that it just misses the shadow. Then, he can ask how far along the moon's circle it would be from the node. Ptolemy comes up with a value of 12¼ degrees. This is how far away the true moon could theoretically be from the node and still result in an eclipse. But calculating the true position is such a hassle. Wouldn't it be easier if we could do a quick sanity check first, using the distance from the nodes at mean opposition? This was the point of the table of conjunctions and oppositions we created a few chapters ago. That gave us the position of the sun and moon about their various circles at mean opposition. So Ptolemy considers how far away the moon could be from the node for mean conjunction or opposition, and it still be possible for there to be an eclipse. Based on the motions of the sun and moon, he determines that the window to either side of the node is actually about 3 degrees wider than if we only considered true oppositions. Thus, if the moon is within 15 1/4 degrees to either side of a node when we do our first check from the table of oppositions, we'll need to proceed further. If it's not, then an eclipse is impossible, and we can quit right there. Ptolemy then turns to solar eclipses and asks a similar question of how far from the nodes the moon could be and still result in a solar eclipse. However, because of the large effect that parallax plays, the analysis here becomes significantly more complicated, and we have to consider 2 scenarios. One in which the moon is to the north of the ecliptic, and another where it lies to the south. The reason for this has to do with the fact that, as we found, the direction that the moon appears to move due to parallax is always away from the zenith. Ptolemy really only considers an observer in the northern hemisphere, for whom the zenith will generally be north of the ecliptic. This means that the parallax will push the moon towards the south. As a result, when the moon is north of the ecliptic, parallax actually makes it appear closer to the ecliptic than it otherwise would. This can result in an eclipse occurring when it otherwise wouldn't. However, if the moon is already south of the ecliptic, parallax will push it further south, making it harder to have a solar eclipse. Ultimately, Ptolemy determines that, for the latitudes he's considering, the moon can be about 20 2/3 degrees from the nodes when the moon is to the north of the ecliptic, but only 11 1/3 degrees when to the south. This chapter was pretty long, but we can sum it up by stating that Ptolemy's goal in this chapter was to determine how far from the lunar nodes the moon can be, and there still be either a solar or lunar eclipse. Since we can quickly find the distance of the moon about its inclined circle from the northern limit, we know how far from the nodes it will be, and can rule out the possibility of an eclipse in most cases without the need for further calculations. In Chapter 6, Ptolemy is now going to ask, if an eclipse were observed, in what period of time will it even be possible to have another eclipse? This really builds on the work Ptolemy did in the last chapter, so let's now draw out a diagram to help us. Here, I've drawn the lunar path looking at it from above. This way we can see both of the nodes at the same time. As we determined for lunar eclipses, the window in which eclipses are possible is about 15 1/4 degrees to either side of the node for lunar eclipses. Sketching the window where this is possible looks like this. For solar eclipses, it was a bit lopsided, as eclipses could happen 20 2/3 degrees from the node when the moon is to the north of the ecliptic, but only 11 1/3 degrees when to the south. Thus, the window in which the solar eclipses are possible looks like this. What Ptolemy asks in this chapter is, if an eclipse occurs in one window, is it possible that, in some number of synodic months, that the sun and moon will be in an eclipse window again, thereby making it possible to have another eclipse? For example, Ptolemy first considers a period of 6 synodic months. In that time, the amount the moon moved about its inclined circle, beyond complete revolutions, is just over 184 degrees. Thus, it's not hard to see how, if we begin in the eclipse window near one node, we can easily be in the eclipse window near the other node 6 months later, regardless of whether it's a solar or lunar eclipse. This is a particularly easy case, but the other intervals Ptolemy considers are significantly more complicated. In some of them, the sun and moon come close to making it back to the eclipse windows, but don't quite make it, based on those mean motions alone. For those, Ptolemy also checks to see if choosing specific points in the orbits of the sun and moon would help improve things. We've also ignored the effects of the various anomalies of the sun and moon, and with solar eclipses, we'd need to also take into consideration the effects of parallax. Overall, Ptolemy considers whether it's possible to have lunar eclipses 5, 6, or 7 months apart, as well as 1, 5, 6, and 7 months apart for solar eclipses. For most of these, Ptolemy concludes that eclipses happening in these intervals is possible. The only one he concludes against is 2 lunar eclipses happening 7 lunar months apart. For solar eclipses separated by 1 month, he concludes that it is possible, but the eclipses would not be visible from the same location on Earth. Although I've breezed through this chapter pretty quickly, this is actually one of the longer chapters, as all the complications Ptolemy considers to thoroughly explore whether eclipses may be possible in certain intervals gets quite involved. But the key takeaway here is that if you begin considering all the possible syzygies where an eclipse were possible and knew one in which an eclipse actually happened, you could rule out a large number of subsequent syzygies without doing any further check, simply because eclipses in that interval aren't possible. So far in Book 6, we've had a fair amount of discussion about when you don't need to bother going through the motions to calculate whether an eclipse would happen, because we already know it's not going to be possible. But Ptolemy has finally run out of times we can rule out needing to check. As such, Ptolemy turns his attention to making the calculations that we do have to do as simple as possible. And as usual, that means making quick reference tables, which he describes the construction for in Chapter 7. He previews things by telling us that we will be constructing 4 primary tables. 2 for solar eclipses, and 2 for lunar eclipses, in each case, 1 for the moon's greatest distance and 1 for its least distance. For these tables, Ptolemy constructs them based on the number of digits of obscuration, where a digit is 1/12 of the width of the sun or moon. By knowing the angular diameters of each of the objects, Ptolemy is able to determine how far away from the nodes this can occur, allowing him to create columns related to this, which are actually what a user would look up, since that's what they'd calculate from the model. Lastly, he calculates the distance the moon would have to travel from the moment the eclipse starts until halfway through, which he refers to as the minutes of immersion. But this is really measuring arc minutes. For the lunar tables, Ptolemy also includes a column that tells us how long it is from the moment that the moon is fully eclipsed until mid-eclipse, which he labels half totality. It should be noted that because the moon's angular diameter can be larger than the sun's and the Earth's shadow is certainly larger than the moon, it's possible for the number of digits listed in the table to go past 12. With that being completed, Ptolemy then creates another little table. Since our solar and lunar tables were each calculated for the moon at least and greatest distance, we need a convenient way to estimate between them when the moon is at intermediate distances. Here, Ptolemy ignores the changing distance of the moon caused by the deferent being moved further and closer from his upgrade to the lunar model, and only considers the motion about the epicycle. Thus, the first two columns are related to the distance of the moon about the epicycle from apogee. Then, the third column essentially tells what percent it is linearly between the furthest and closest approach due to the epicycle. This lets you know how to proportionally estimate between the values given for the nearest and furthest distances in the previous tables. With this done, Ptolemy notes that many who observe eclipses measure the size of obscuration not in the diameter of the disks, but on the whole, by the total surface area of the disks. In contrast, Ptolemy has been measuring eclipse digits. This would presumably make comparing eclipses between Ptolemy and other sources rather difficult without some way to translate between the two. Thus, Ptolemy creates a handy table that lets us do just that. These tables are then given in Chapter 8. With that done, we have everything we need to be able to actually calculate eclipses. Ptolemy begins with instructions on how to use everything we've done up until now to calculate lunar eclipses in Chapter 9. As usual, Ptolemy doesn't provide a worked example, but does walk us through the steps. First, we need to determine when we want to check for an eclipse. We can then head to the table of oppositions from Book 6, Chapter 3, and look up the number of years and months corresponding to that amount of time since the beginning of the epoch. This will give us the amount that the sun moved from apogee, the argument of lunar anomaly, and the argument of lunar latitude. This gives us information about the arrangement of things at mean opposition. But we need to understand the true opposition to see if an eclipse will happen. The method for which to do so we explored in Book 6, Chapter 4. There, we learned that the true opposition can be determined by figuring out how far away the moon was from the Earth's shadow at the time of mean opposition, and then figuring out how long it would take to close that gap, factoring in the fact that the shadow will be moving too since the sun moves. Thus, we will have to look up the actual lunar anomaly from Book 4, Chapter 10, and apply it to find the true position of the moon at the time of mean opposition. Similarly, we need to find the amount of anomaly that the sun has from Book 3, Chapter 6, and factor that in as well. The difference between these tells us the size of the gap before taking into account the moving shadow. But since we've learned a method to determine how to account for that, we can then determine the total distance the moon will have to travel to bridge the gap, taking that into account. That then gets added to the argument of latitude to figure out if the moon is in the eclipse window. If not, we can quit right there. If so, we can then proceed to look up that argument of latitude in the lunar eclipse table from the previous chapter, which tells us how much the moon would be eclipsed, if the moon were at its maximum or minimum distance. Next, we need to estimate between those two. That's done using the table of corrections we just created based on the position of the moon about its epicycle. Ptolemy leaves out a fairly important piece of information here, as the position about the epicycle, also known as the argument of anomaly, that we looked up, was for the time of mean opposition. He doesn't remind us that this needs to be adjusted for the time of true anomaly, but knowing how far the moon had to travel to bridge that gap, we can estimate how long it took the moon to bridge it in ecliptic longitude, and again use the lunar anomaly table to look up how much the moon would have advanced on its epicycle in that time. That will give us the argument of anomaly at the time of true conjunction, which we can then look up in the correction table to understand as a proportion of the epicycle's radius, how far the moon was at that time due to its epicycle. With that in hand, we take the difference between the values from the table of oppositions and the eclipse tables, apply that proportion, and determine the true parameters of the eclipse from the tables. Ptolemy then tells us that we can use these to determine some further information. So far, we've only calculated the eclipse at its greatest point, but using the arc minutes of immersion, we can determine when the eclipse began and ended. Thus, we can get a comprehensive picture of how the eclipse plays out. In Chapter 10, Ptolemy discusses how to calculate solar eclipses. The process begins the same. We determine the conjunction for which we want to see if there is an eclipse and look up the values of the sun's motion, the moon's anomaly, and the moon's latitude. We then determine the gap between the mean conjunction and true conjunction and figure out how the positions of the sun and moon would have changed at that time. But after that, the processes diverge slightly because we now need to take lunar parallax into consideration. Here, we must take into consideration the precise time of true syzygy. However, that time is reckoned from the longitude of Alexandria in modern-day Egypt. Thus, we have to take into consideration the difference in time between Alexandria and the observer to determine the local time. Being more specific, that would give us the mean local time. We haven't talked much about timekeeping, but noon is defined as the moment when the mean sun crosses the ecliptic. But as we've learned, the sun has an anomaly, which means it will generally not arrive at the meridian exactly at the mean time. At any time except apogee or perigee, it will either cross the meridian early or late. Combine that with the fact that the sun is higher in the sky in summer and lower in the winter, and you get a complicated dance that can shift the timing with which the true sun reaches the meridian by as much as 15 minutes in either direction, which is known modernly as the equation of time. Although Ptolemy doesn't use this term, he does say we need to take this into account. Why is he so picky about getting the timing exactly right? Well, using the time plus the ecliptic latitude at true conjunction, we can look up the distances from the zenith in Book 2, Chapter 13 to determine the amount of parallax. But recall that parallax is always directed away from the zenith, which means that the displacement can have components in both ecliptic longitude and latitude. Thus, we will need to disentangle these. To do so, we'll need to understand the angle the great circle between the zenith and the moon makes with the ecliptic, a value which is highly sensitive to time, hence Ptolemy's focus on it. Fortunately, once we know the precise timing, looking up the angle can be done easily as it's part of that same table from Book 2, Chapter 13. Once all that is disentangled and we finally know the distance from the node at the time of true conjunction, we can check to see if that falls within the range possible from the eclipse tables. If it does, we then know, from this table, how many digits the eclipse is, as well as how many arc minutes of immersion there will be from the beginning to mid-eclipse. At this point, we've learned how to check various syzygies to see if there will be an eclipse, and if there is an eclipse, we now know a good deal about its nature. But Ptolemy isn't quite finished yet. For the remainder of Book 6, we're going to explore something known as the inclination. This is a rather bizarre concept, but involves imagining a great circle drawn between the sun and moon for a solar eclipse, or the moon and the center of the Earth's shadow for a lunar eclipse, and then asking how that intersects the horizon or ecliptic. This isn't really useful for astronomical purposes. So why does Ptolemy get into this? The answer is that it likely had to do with what was known as pronusis, which is important in astrology, particularly Hellenistic weather astrology. Although the Almagest doesn't explicitly discuss astrology anywhere, this is a pretty clear nod towards it, given that there is no astronomical use for this. We do know that Ptolemy was an astrologer as well, as he was also the author of an astrological text known as the Tetrabiblos or Quadripartium. However, Ptolemy's treatment of the inclination in the Almagest is fundamentally flawed. Essentially, Ptolemy is going to try to break the inclination into two parts. The first is the angle between the great circle between the eclipse centers and the ecliptic, and then the arcs that the ecliptic cuts off along the horizon from due east and west. If an eclipse were happening directly at an observer's zenith, this could work out, but for most latitudes, including Ptolemy's own latitude in Alexandria, this would never happen. Ptolemy glosses over this, but evidently the problem was well known in antiquity, even to Ptolemy, who attempted to correct it in some of his other works. Regardless, Ptolemy begins the chapter by telling us that trying to calculate such things precisely is extremely difficult. As such, Ptolemy recommends simply watching the eclipse live and calculating based on actual observations instead of theoretical considerations. Ptolemy then tells us what moments in an eclipse are the most important: the first and last moment of the partial phase, the start and end of totality, and the midpoint of totality when immersion is the greatest. Next, Ptolemy discusses the intersection of various great circles with the horizon. This section feels somewhat out of place as the definitions he gives are rather self-evident to anyone who's been following along so far. This makes me suspect that Ptolemy expects that readers may be reading just this section, likely for astrological purposes and skipping the rest of the work. Nevertheless, he defines the point on the northern horizon where it intersects the meridian as the north point, and in the south as the south point. Then he notes that the points of the zodiac that are the equinoxes always rise due east and set due west. These are called the equinoctial rising and setting, respectively. The points of the solstices get called the summer rising and setting for the summer solstice and the winter rising and setting for the winter solstice. These solstice points will create some bounds on the horizon which mark the range north or south of due east and west that the sun can rise. But what are those limits? Ptolemy tells us that we actually learned how to calculate those in the first books of our treatise, which is referring to Book 2, Chapter 2, which was devoted to this topic. However, we never actually created a handy reference table like we usually do. Instead, Ptolemy tells us he's going to do that now, although since he's already instructed us on how, he doesn't explain again. Instead, he just explains how the table will be laid out in the next chapter. Ptolemy then returns to the angle I mentioned at the beginning of this chapter, the angle between the great circle drawn through the moon and sun, or Earth's shadow, with respect to the ecliptic. Ptolemy then declares that he will calculate this for increments corresponding to a difference of 1 digit in obscuration, but only for lunar positions at the mean distance. He considers that sufficient for whatever astrological purposes motivate this. To make this calculation easier, he makes the assumption that the moon's path is parallel to the ecliptic, which, over short distance, is reasonably true. This allows him to create a sketch of the moon at the various important positions he mentioned earlier. Then he can geometrically work out, at each of these points in time, the angle in question. The tables Ptolemy promised are then delivered in Chapter 12. I especially like the table for the angles along the horizon, as this one is given in a novel radial pattern. The second table, for the angle of inclination between eclipse centers and the ecliptic, is given in a more standard table. In the final chapter of Book 6, Ptolemy explains how to use the information we've just worked up to calculate the inclinations, although he still doesn't really explain what these are used for. First, we need to calculate the various parameters of the eclipse as instructed in Chapter 10. Then we find what points are on the horizon at that moment, although Ptolemy doesn't explain how. Next, we use the radial horizon diagram to figure out how far those points are from east and west. Lastly, using the inclination table, we can determine the angle between the great circle through the eclipse centers and the ecliptic. Finally, the great circle through the eclipse centers will intersect the horizon at 2 points. So, Ptolemy tells us which ones are the important ones based on whether the moon is north, south, or on the ecliptic. And that finishes out Book 6. This was a very challenging book, so let's answer the question that I posed at the beginning. How do we use what we've learned to predict eclipses? The answer is that we begin by recalling that eclipses only occur at syzygy. Finding the true syzygies is tricky, so Ptolemy told us to begin with the mean syzygies, which happen with a much more easily predictable timing, which Ptolemy helped us understand by constructing a table that informs us when they occur. Thus, if we want to predict eclipses, we could start with a list of possible syzygies that we should investigate. Fortunately, we don't have to investigate every syzygy because many of them won't happen close enough to a node for an eclipse to be possible. Thus, if we know when the last eclipse occurred, we can rule out several other syzygies and save ourselves a lot of work. If we do need to investigate the syzygy, Ptolemy provides everything we need for the calculation. From the table of conjunctions and oppositions, he handily provided the key figures for how far the sun and moon will have advanced about their circles. We can then make some adjustments to account for the difference between mean and true opposition to see if things fall within the eclipse window. If so, then congratulations, you found an eclipse. And you can perform a few additional calculations to figure out the details about it. And now that you've found an eclipse, you can begin the process again, skipping several syzygies in hunt of the next one. Using methods like this, astronomers were able to forecast eclipses. These were often published in ephemerides like this one from 1533. In it, we can see the wonderful illustrations of the eclipses predicted by Luca Garrico. If that name sounds familiar, it's because he was the chief instigator of the 1524 flood panic. But with this, we're pretty much finished with the sun and moon, although the lunar model does pop up again in the future, as Ptolemy will use the position of the moon to help determine the position of the planets and stars to calibrate his planetary models when we get to those. Before we do that, we'll need to explore the fixed stars, as Ptolemy is going to need to use those to help him determine planetary positions. But we'll get to that in another video as we continue to explore astronomy before the telescope. Hi everyone, thanks for watching. Not only was Book 6 among the most challenging books of the Almagest, but this video has been the most challenging one I've yet recorded. My intention was to have this one out about 2 weeks ago, but I had to come back and re-record major sections at least 5 times as I discovered things weren't working, as I was editing and had to rewrite parts of the script. Obviously, these videos take a lot of effort to create, and if you'd like to support that effort, I recommend checking out my Patreon. The higher tiers get access to scripts for most of the videos, which often feature detailed bibliographies and copies of all of my notes from research for that video. That's not the case for this particular video because there's really only one source, the Almagest. But if that's more than you're interested in, thanks for watching anyway, and I'll see you next time on Astronomy Before the Telescope.